All right, gang. Well, let's see. Yep. Welcome to Monday the 13th. Not quite as scary as Friday. Um, Hopefully, you're all going out to try to see the comet. So, some comet called Neowise, which is apparently viewable best at like 4 in the morning. So, you know, Colorado guys are already up by then. Might as well just go look out the window. Low on the horizon, and then I think in the evenings, if it's not too cloudy, you can see it as well. So even without a telescope. Um, okay, so let's see where we're at. Test 3 is tomorrow, so that's 14 July, and it covers 11.45 and then 12.1 through 6. So it's quite a lot, actually. If you have been working on the homework, good. If you haven't, it'll be interesting tomorrow. So what I did was I went through all the homework that was turned in, and I think what we should do is start by going back over some of these things just to refresh your memory and some of the problems we didn't quite get. But and then along the way, if you have questions on anything else, please let me know, and we will go over them. So let's see. So 11.4, number 25. So 11.4 was on the T n a sub t, a sub n. So it's all about the tangent and normal vectors and how they break down the acceleration vector into different components. This one was not algebraically too difficult. In fact, r of t is just the parabola t and t squared. On the interval from -1 to 1, and then the question is figure out these things when t is 0 and when t is 1. So sort of on the on the picture, what's happening. So you had the parabola, you know that as we go from -1 to 1, this thing does what a parabola does. So -1. So we're moving moving along the parabola. And so you could draw the tangent vectors at every time. The normal vectors are going to point towards the middle because, again, the normals will tell you how it turns. It's like pushing on it and making it turn. So that's the pieces there. So there's tons of formulas that are going on in that section. So I think, let's see, this is on page 2. Well, the definition is on previous pages, but sort of the key ones are on 669 to get the a sub t and the a sub n. But as a recall, we do need r prime. So we need, which is v, so there's our velocity, 1 and 2t. We also, so that's v, we also need a, probably. We'll just do it. And it's pretty, that one's easy, so just 0, 2. So the acceleration vector is always pointing down or up. Maybe that makes sense. We do need, I think, the length of v. So the length of v is the square root of 1 squared plus 2t squared. So that'll be 1 plus 4t squared. So it's the length of that vector. And then we can use the formulas on page 669 again. And there's a couple different versions, but one of them is the tangential component of acceleration. The acceleration vector is just 0, 2, but it can be broken down into the tangent vector, some multiple of the tangent vector, plus some multiple of the normal vector. And that's exactly what these are, the multiples. A sub t and a sub n are the multiples that we would use. So a sub t says you can take the derivative d by dt of whatever this velocity length is, or the speed. So you take the length of, take the absolute value of velocity before you get speed. Now you take the length, and this will give you speed. So we take the derivative of that, hopefully not too bad, and we will get 4t over the square root of 1 plus 4t squared. So you rewrite that as 1 plus 4t to the negative a half, or to the positive a half. You take the derivative, half comes down, it becomes 1 plus 4t squared to the minus a half, which means the square root will be shifted to the bottom. You take the derivative of the inside, which will be 8t, but you also have that half that came down from the derivative. So that's the tangential component, depending on the time and the position that you're at. A sub n can be gotten in a couple ways, but one formula is you can take the square root of the length of the acceleration vector squared minus this previous number, a sub t squared. So we know a, so we got that. Maybe we should just even put it here. The length of a, that's pretty easy, that's just 2. So that means we can take and put in the length of a, so that'll be 2 squared. You can take the length of, or the at squared. Let me shut that down for a second. So minus 4t over the square root of 1 plus 4t squared. And that's the formula for a sub a. And if you wanted to work it out, you could. It does come out to be fairly nice. That's just 2 over the square root of 1 plus 4t squared. But you also have to know in the context. The context is just find those when t is 0 or when t is 1. So if you plugged it into the first formula and worked it out, it's the same as if you plugged it into the second one. It's just how hard is the algebra. So when t is 0, for example, then you just plug in t equals 0 into each of these cases. And a sub t will be 0, because I'll get 0 over 1. And a sub n will be 2. Yeah. And so in the picture, the idea is, something's happening up here where it's probably slowing down, and then at the origin, you've got the tangent vector that points that way, and you have the normal vector that's pointing that way. And because the tangential component is 0, that means that there is no speeding up happening there. It's all turn. It's all causing it to turn. At t equals 1, then you're at the end, so you can talk about the tangent vector and the normal, and it's probably not going to be quite vertical there, so didn't mean that kind of thing. The tangential component will be, well, you just plug it in, and you'll get 4 over the square root of 5, and the normal component will be 2 over the square root of 5. So there is some part which is causing it to speed up, and there is some part that's causing it to turn. So that's what those a sub t and the a sub n mean. If it's positive at, that means it's going to be speeding up. If it's negative, then it's going to be slowing down. You probably also notice that if you take a sub n, it's a square root of other things. So the an will always be positive. It's either going to cause it to turn one way or the other. You're not going to have a negative normal component. So that's the idea. So that's number 25 on 11.4. So it brings to bear several things. Get your mind back into it. It doesn't help you actually find what t and n are, but you can go through the algebra and the formulas on that. And again, remember that if you know it's 2D, then there's an easy, once you know t, you can get n very quickly by just reversing the components and putting a negative on whichever one causes it to go towards the inside of the curve. So instead of going through all the algebra finding t, and then, which is hard enough, but finding n can be difficult. So there are little tricks in 2 dimensions. Not going to remember that. Let's see what's next. 11.5. Where am I? 11.5, number 29, I think. Right. So again, the algebra on this will not be too difficult, but at least it'll be a nice reminder of how this works. So you have a curve. What am I doing? That's the wrong one. Okay, 29 is cosine t and 3 sine 3t. So I don't know exactly what that looks like. The question is at t equals 0, find what's called the radius of curvature, which we know is just the reciprocal of whatever the curvature is. So we need to find k. So find the curvature for this problem. Right, okay, so curvature, that's what you think it is. It tells you how curvy things are. And so the formulas for this kappa, page 677, there's a couple different versions depending on the form of your function here. So one of them, number 3, the curvature says it's r prime cross r double prime. You take the length of that and then divide it by the length of r prime e. So that's going to be the one that you're going to want to use on this one here. The other two is it's like y equals some function of x. And I think it'd be probably difficult to get rid of the t's in this equation just because you have this 3t. But regardless, we can use this formula that says we need r prime and we need r double prime. So r prime is negative sine t, and then, sorry, this 3 isn't here. It's the sine of 3t, but not 3 sine. So, sorry. So we do take the derivative of that, we get 3 cosine 3t, the second component of r prime. And then r double prime is going to be, take the derivative of that, which is going to be minus cosine. And then the other one will be 9 sine, and it'll be negative because it's the derivative of cosine. So remember to pick up that extra multiple of 3 in each case. So all we need to do is just figure out the length of r prime, that goes on the bottom, and then find the length of r double prime cross r prime, and that goes on the top. So to jog your memory some more, the cross product of this guy, and you're like, wait, there's no k's. So realize that, yeah, there are no k's, so those components are going to be 0. That also tells you that this thing is only in 2D, so if you do the cross product, the answer is going to be only in the z direction. Because the only thing that's perpendicular to both of these two guys would have to be a k component coming out of the plane. So we plug in r, we plug in r prime here, and we end up getting just like the little subdeterminant for k. So that's going to be 9 sine t sine 3t, and then we'll have back the other direction. It would be plus 3 cosine t cosine 3t. If I do that now, let's see, negative, so this would be minus sine 3 cosine minus cosine minus 9. So it'll be plus, that'll be plus. And then that's that, but that'll be k. But again, when we take the length of something that only has a thing times k, it's just going to be that answer inside, maybe absolute value. The length of r prime would be the square root of each of those components squared, making sure to square out any negatives. So sine squared, 9 cosine squared 3t. And so then we take the length of r prime divided by the length of r prime, and then at t equals 0. We're not filling in quite all the details here. Plug in 0 for the cross product, and the first part drops out because it will be sines of 0. The second part will be 3. So we get 3 on the top. And then on the bottom, we plug in 0, we'll get 0 plus 9. Take the square root, that's 3, but then the 3 gets cubed. So the formula says you cube the answer for that. So I'll get 1/9 is the curvature, which means that the radius of curvature is just 9. So the curvature is very small. 1/9 is pretty small, which means it's not curving very quickly. And that's because it's equivalent at that point to kind of thinking that it's the same thing as a circle of radius 9. So it's like roughly that level of curvature at that point. You could plot it out. I'm not going to, but at least that's the calculations for it. So at this point, again, the curvature is kind of like computing the curvature of the circle, because that's the circle that best approximates it at that point. Okay, 12, chapter 12 here. 12.1, number 19. Okay, so this does get tricky because it's in 3D now. So we don't. It's hard to know exactly what the plots of these things look like. So let's see, 2x minus 2y over x squared plus y squared plus 1 is that's your z. So plot that, and it's not easy because you have to make a big chart. You got to plug in x, y, figure out z, plot the 3 points, and then it's going to end up being some sort of surface in 3D, and that's hard to do in your head, I think. So what they do is they say, well, let's look at the level curves and make our topographic map, however you pronounce it, at different levels. And they use the letter C for some reason. I'm not sure why. That's pretty common. So look at 3 different levels on this thing. What does the topographic map look like when you're 1 unit negative elevation on flat, and then 1 unit elevation up? And then maybe once you get those 3, you might be able to piece them together. So what that means is you just set z equal to -1, z equal to 0, and z equals 1, where you're using now f and z interchangeably. So I get -1 equals 2x minus 2y over x squared plus y squared plus 1. And then you just have to unravel out, well, what does that curve look like down in 2D now? So let's see. Well, do some algebra here. We can cross multiply and we'll get -x squared minus y squared minus 1 equals 2x minus 2y. So just again, cross multiply. I don't really like having all those negatives in there, so let's just multiply by -1 everywhere. So we'll get x squared plus y squared plus 1 equals 2y minus 2x. So basically just reversing all the signs. And then if we bring this stuff to the other side, we'll get x squared minus 2y. No, I want to do the x first. 2x plus, or x squared plus 2x, and then I'll have a y squared minus 2y. And if you get to this point, you're like, it looks like I'm probably going to have to complete the square. And so it's move and complete the square all in one step here. So I'm going to have to add 1 here. I'm going to have to add 1 here. I've already got the +1, so I really just need to add 1 to the other side. And so I'll get x plus 1 squared plus y minus 1 squared equals 1. And that's a circle. So that says it's a circle at -1, 1 of radius 1. So that's the level curve, and z is -1. So okay, so we have one level curve so far. And then you just repeat that process as many times as you need in order to try to then figure out where are the hills, where are the valleys, and how does it all piece together if you try to do it in 3D. So I'm just going to do the other 2. I'm not going to try and piece it all together, but maybe you can do that. If we try the level curve c equals 0, then that one just says that 0 equals 2x minus 2y over x squared plus y squared plus 1. That's the fraction, so setting it equals 0. Well, the only way a fraction is 0 is if the top is 0 and the bottom's not 0 at the same time. The bottom's never 0 because it's all positive numbers. So that means the top has to be 0. But how do you make 2x and 2y subtract to be 0? That means that x has to be y. And so that's just our line, y equals x. So that's what the level curve looks like there. And then finally, if c equals 1, then we get 1 equals 2x minus 2y over x squared plus y squared plus 1. And if you unravel that out, you actually also get x, you'll get x minus 1 squared plus y plus 1 squared equals 1. And then that's the circle as well, but now a new center at 1, negative 1, and radius 1. So if you put these three things together, you get a circle here, and z is minus 1. You get the line y equals x if z is 0. And then you get this circle if z is 1. So this is down low, this is on the flat ground, and then this is up high. And you can just keep unraveling it. I think what ends up happening is the circles get smaller and they kind of move in as long as you're going up and down higher. If these were fractional values, good question, probably gets bigger. So I don't know. In 3D, it's kind of funky, but those are called level curves for that particular problem. Yeah. So that's the idea on that. If you can't piece them all together, then your brain works pretty good. Okay, 12.2, number 16. All right, so now we're talking about things that look like this. The limit as xy approaches some point, and in this case, it's the point 0, 0. I don't know why I didn't just write that up there. Maybe I will. Okay, so limit xy goes to 0, 0 of this fraction x, sorry, x is plus and minus. Yeah, x plus y over x minus y. So that's your z function. So you should think that if you were to plot this, you'd have x plus y over x minus y. There's your function. And then the deal is that the domain, you have to have that x and y are not the same, because if you had x and y the same, then the denominator would be 0. So if you tried to plot what that looked like, that means here's x equals y, but you don't include it, but you can do any point above and you can do any point below. So just everything except for things on the line y equals x. So this is an unbounded domain because there's no fence you can put around it. And it's open because it doesn't include this boundary value. It's a dotted line. So this is an open, unbounded set. 0, 0 is certainly not included in here because I couldn't put in 0. In fact, the top would be 0 as well. So in Calc 1, when you're like, well, if I got 0 over 0, then I could use L'Hopital's rule, right? And the answer is no, because there is no L'Hopital's rule in 3D. Darn it, doesn't work, only in 2D. Okay, so what do I do? Well, I consider different approach paths. So I want to come into 0, 0 from any of these like shaded regions, and you can come in infinitely many directions. So the only way this limit's going to work is if you do the limit from one direction and another direction and another direction, and all the directions are the same. They have to all be the same in order to work out. If you can get some that are different, then that means there is no limit, and it's then going to be broken. It's already broken at the origin. I don't even know what it looks like, but it could be badly broken. So let's see. Well, if we try path number 1, and this is not quite the homework problem, but that's all right. If I come in from path number 1, then what does that mean? That means I'm picking values that are getting closer and closer to 0 along that route. So along that route, y is 0 because it's on the x-axis. And at the same time, x is going to 0, but I'm plugging in positive values for x. So if I do that, then I impose that on that limit, and it then becomes the limit as x goes to 0 of x plus 0 over x minus 0, because y is 0, so I'm using that. So, what do we get? We get the limit as x goes to 0 of x over x. Yeah. So, but whenever you have a fraction where the top and the bottom are the same and you don't have 0 over 0, you can basically cancel them and you'll get 1. So if you were coming in from the right like this, you would end up 1 unit high. That's where you would be heading. And that's what that says. So maybe the answer is 1. Well, let's try a different approach path. And we come in from the top. So that means from the top, x is 0, but y is going to 0 from positive values. So what happens when we stick in that, we get the limit as y goes to 0 of 0 plus y over 0 minus y. And in that case, when you have y over negative y, that limit will be negative. So that's no good. If I came in from the top, it would look like I was supposed to end up 1 unit down, 1 unit into the board, z value. So right off the bat, we know that there is no limit because I got 2 different answers from 2 different directions. Now the homework actually just says, well, let's try an approach path that looks like this, y equals mx. So that's just a line of different slopes. So you just pick a slope and you come in y equals mx. So this is like approach path 3 if I came in from this direction. So what would that look like? Well, I don't know exactly the rest of this. So let me try and at least impose this. I get x plus mx over x minus mx. And we'll put in this bottom limit part in a second. We know something's going to 0. But the point is what do we have here? All the x's can be canceled out, and we get 1 plus m over 1 minus m. So the answer is going to be 1 plus m over 1 minus m. Sort of regardless. I mean, technically x is going to 0 in all of these cases. And it actually doesn't, I drew the line coming this way, but it could be any line except for y equals x, because I can't come in along the dotted line. That's no good. But any other line I come in, the answer to my limit is going to be 1 plus m over 1 minus m. So if I pick every different slope I pick, I'm going to get a different answer for my limit. So every different approach path gets a different answer. So this limit can take on probably any value you want, depending on which line you're approaching. So it gets weird. And we just say the limit doesn't exist. Limit doesn't exist, or you write an empty set symbol or something like that. So that's that one. Maybe one more, and then we'll see if you have questions on recent homework or 12.3. Right, so 12.3 is on these guys, partial derivatives, fx, fy, fxx, fyy, fxy, and which is, by the way, the same as fyx for 99% of the time. Your time, 100% of the time, I think this will happen. We may come up with like one weird example, but I wouldn't probably worry about that too much. So given a function, being able to find these partial derivatives is one thing. The tricky part is what happens if we're given the derivatives and you have to find the function. So basically it's like question mark function up here, but when you found the x derivative, you got x plus y. And if you find the y derivative, then you also get x plus y. This is number 28. You're like, that's kind of weird. Well, let's see. So I think in this case, it's often sort of either guess and check or try and take the derivative backwards, so antiderivative. But realizing that when you take an x derivative, anything that has a y in it could go away. So when you anti-differentiate in the x direction, you're going to pick up some stuff, not just plus c, but like plus c's and plus just y's. And when you take the antiderivative for y, you're going to not only get plus c's, you're going to get like plus c's and plus just x's. But that has to be balanced with when you do the derivative back the other direction, that those things either cancel out or they give you the things that you need to make the partial derivative work. So I think this is definitely one that you have to verify. You just gave the answer and went, well, this is this and this is this, so I put them together and there's my answer. Did you check? no. Well, let's check, and you got it wrong. And this is such an easy one to check that, you know, do it. If you get it wrong and you just didn't check it, then I'll just get a 0. I don't just like think about it. Now, what do you take the derivative of with respect to x to get x? Well, that looks like it should be 1/2 x squared. Because you take the derivative and you get x. That's the whole point of that. The slightly trickier one is you would get, to take the x derivative to get y, that looks like xy. So remember, think y is constant on that. So that's how that would work. But remember, you're also going to get like plus c, and you're going to get some like just y terms in there. And what are those? You cannot know these just from the left side of your answer. So, you know, maybe temporarily you put that aside and you're like, well, let's try the other side. What would cause my x to occur if I did a y derivative? Well, that also looks like xy. Okay, I know that. And then how about y? I will get 1/2 y squared. That's that one. Okay. And then I'm going to get like plus c, and I'm going to get some just x terms if that happens. So now what you have to do is you have to put these together. So you put them together, and you can't just like necessarily just really just put them together, like add everything up and we're done. Because if you put xy and another xy together, so if you just put them straight up together and got 2xy in your answer, suppose that was part of your answer, now take the x derivative of that. If you did the x derivative, you get 2y. Is the x derivative have a 2y in it? No. So that means that putting them just straight up, adding these things together does not work. You have to, like, there's some overlap, like a Venn diagram kind of thing. So the fx, I know, has to have a 1/2 x squared in it to get the left side. Am I worried about that on the right side? And the answer is no, because I know that when I did my y integral, I would get some x terms. And that is just an x term. When I take the y derivative of that, I get 0. So it will not appear in the y derivative, and it doesn't. So that's good. Similarly, I'm going to have a 1/2 y squared, and that is because of the right-hand side when I do the antiderivative. Am I worried about that on the left? No, because I know I'm going to get some y terms, and when I take the derivative of that 1/2 y squared in terms of x, it goes away because it's a constant. So that sort of works out, takes care of that one, takes care of that one. What about the xy? Well, it turns out that's like the Venn diagram overlap. So just xy works for both. If I take the x derivative, I get y. Ooh, that's good. If I take the y derivative, I get x. Oh, that's the first part of the second one, so that works out really well. So that covers everything, and we always are going to have maybe a plus c in there. And there you go. And check. Take the x derivative, you get x plus 0 plus y. That's good. I wanted to get x plus y. Take fy, you get 0 plus y plus x. Check, check. Those two work, so therefore, here's my answer. So it really is just take the antiderivative both ways, but then figure out how to Venn diagram them. Maybe it's kind of like thinking about fx and fy. The Venn diagram has totally 1/2 x squared on one side, totally 1/2 y squared on the other side, but then you have xy in the middle, and that's the shared one. So it's not like double; it's the shared one. So if that makes sense, good. If you need more, well, I'm just gonna go ahead and do it. What about 29? One we haven't done at all. Fx equals 6xy minus 4y squared, and fy is 3x squared minus 8xy plus 2. And now how do you recombine those in order to get one function? Like, where did they come from? Those are the derivatives. What's the function? So you just try separately here, and then we'll try and piece them together. So if this was the case, and I think as far as like an x integral, the function should be 3x squared y, because that's how you get 6x. And this one would be 4xy squared. That's how you get that one. Then you're going to have some y's, and you're going to have a plus c, and I'll figure out what that is in a second. Over here, if I did a y integral, this integral dy, then this should be like 3xy squared. That one. This one should be minus 4xy squared. Yeah, that looks good. And then this one would be 2y. And then we're going to have some x terms, and we're going to have some plus c terms. And then we just have to put these two things together. And now this one actually is pretty nice. The shared is actually bigger than the normal part. So you get like this. If the fx and the fy, the shared part would be 3x squared y and minus 4xy squared, because that's in both terms. The thing that only came from the fy would be 2y. The only thing that came from fx, nothing. There's nothing coming from that. So when you put them all together, the function will be 3x squared y minus 4xy squared plus 2y. And then, I mean, technically there's plus c, but there's sort of always going to be a plus constant like that. And then that's it. So, and then you can verify. You do this a lot in Math 311 when you're looking at exact equations to figure out whether it's exact, whether you can use the exact method. You've got to check some partial derivatives, and then you've got to recreate the original function. What are those things called? Conservative vector fields or something like that. I can't remember. I haven't taught that for a while. So anyway, so that is a lot of the previous problems. I think what we're going to do is we're going to cover 12.8, but I also want to make sure that you have time to answer questions or get questions answered for the test tomorrow. When we come tomorrow, we'll figure out whether we want to do the test in the morning or in the afternoon. So think about that. That means like either do new stuff in the morning and then do the test in the afternoon, or vice versa. Maybe think about that over our break here real quick. And then when we come back, we can take a vote on that. And then it's not a democracy. I mean, I'm the emperor here, so I get to make up my mind. But I'll take in my subjects' thoughts on this. So I'm going to have a slight voice in it. So anyway, quick break, and then we'll come back and talk some more about those. And then 12.8. See you in 8:15.